Okay, so this is the review for the final exam. So the exam will not be particularly comprehensive, although some of the things will be, but it's going to focus on the chapters that we've talked about since the midterm, which is basically 7, 9, 11, and 12. Okay. So the format will be similar to last time in that it will be either a problem to solve. Well, I want you to put all the steps in there, or it could be an essay question where I want you to explain um, some aspect of what we've talked about. Okay. And it certainly is fair game to ask questions about the different techniques we've used as far as how we solve the algorithms. Okay. So we're going to go through briefly some things in this video that I think are important. Again, one thing I'll reiterate from the last exam that I'd said in the comments on the exam, I want to make sure that these are your words and not coming from somewhere else. So cutting and pasting from any source is not good. It's plagiarism. It's not what I'm looking for. Okay, so I want to know how you would explain these things. Okay, so don't attribute it. Don't put a citation to another site. Just don't do that. If you need to consult a source, that's okay. Read it, put it in your words based on the understanding of what you've done in this class. And I know people get nervous and want to make sure they've got it right, so they use somebody else's words, and just don't do that. Okay. So we started off here with chapter 7, which is on space and time trade-offs. So the idea here is some ways that we can, we usually have a lot of space, right? Space on computers nowadays, it's cheap. So we have a lot of hard drive space, we have a lot of memory comparatively to what we used to have. And certainly hard drive space we can add more of without too much trouble. So if there are ways that we can do some work in advance and we're able to make the processing go quicker, and that's what we're talking about. Okay, that's what this section is going to be about. Okay, so different techniques we have here. First, we have the counting method, which is a method of sorting. Okay, and we had the Boyer-Moore algorithm for string matching, and its simplified version, the Horspool method. Okay, and remember for that, the one that we did was the simplified Horspool method. Okay. So we also talked about hashing and about indexing with B trees. Okay. So the sorting by counting, the examples are there. Okay. If I ask you for an algorithm in pseudocode, then I want it to look like this. Okay, starting with the algorithm in all capital letters and all that. Okay, and again, if it were me, I would cut and paste one from the book and then change what I needed to change to keep the format the same. Okay, so yeah, all that's fair game as far as the sorting of the array. Okay, the string matching where we talked about all of that. There could be an example of that. Again, we're going to use the simplified Horspool method. Okay, so the shift table and the Horspool matching are all fair game. Okay, Boyer-Moore, I'm not going to ask you that. Okay. We talked about hashing, so you should know about the hash table, the hash function, the hash address. We have the open hashing and the closed hashing. That one uses an array, one uses a linked list. So open hashing uses a linked list where you can't run out of space till you run out of memory. Where the closed hashing uses an array, and that's where you have to do the linear probing or some method in order to if the hash address is supposed to be a 10, and when you're writing it and 10's full, you write it in 11 and so forth. You go to the next open one. Okay, so examples of that, we talked about that. Okay, and then we talked about the idea of the B tree. A B tree is an indexing that we can do on data. Okay, you should have seen this in your data structures class, I would imagine. Okay, it looks like this basically, where this would be a tree of order 4. A tree of order 4, unlike a binary tree, binary trees can only have 2 children. A tree of order 4 can have 4 children. Okay, but that means we can only store 3 bits of data because we have the little connectors or the little children places for the arrows for the children to come out. Okay, we talked about the ways we can do this. It's similar when we're searching for like in a binary search tree, not quite as efficient, but it gets you to, there are fewer levels, okay, because you're indexing basically. So you're taking a linear search along this way to find which of these you go to. You keep going down from there, okay? So certainly be familiar with those and how that works, okay? Chapter 8, we skipped entirely, so nothing to worry about with chapter 8. Again, the summer, you're bored, you have time, it's a good chapter. Nothing wrong with that at all. Just didn't meet our particular needs in this class, okay? So the next thing we talked about, it's a good technique. Greedy techniques, they're pretty useful, okay? I think that they make sense because we try to get the quickest, and it turns out to be a pretty good solution, okay? So again, we start with the change-making problem. So we did an example with that. If you're giving somebody 79 cents a change, the greedy algorithm says, give them the biggest coin that you have first. So if you have a 50-cent piece, you give them that, okay? So you don't start with the penny, okay? You start with the biggest. You're gonna get the biggest bang for the buck, basically, as we go, okay? So that's the idea, okay? So with these, and it has to be either an optimization problem or one that we can put into this kind of a form, because there has to be a better or a worse solution, okay? So when we're looking at these, each step has to be feasible. It has to be locally optimal. It's the best choice among all the feasible choices that you have at that step. And it has to be irrevocable in the algorithm, okay? That once you make it, you're not going to unmake it, okay? So this is not branch and bound that we talked about in the last chapter at all. This is a different technique, okay? So at every step, you're going to take the best option that you have, okay? So they give some examples here that you can go through, okay? The big things here in this chapter, I think, are probably Prim's algorithm to create a minimum spanning tree. We worked through some examples. I think there may even be maybe a video on that, maybe not. But anyway, it's the idea that when you have a weighted graph, which is a graph where each edge has a weight, then you're going to start and then add the cheapest next path until you get avoiding cycles until you get all of the graphs connected. So there's the algorithm in pseudocode for Prim. Okay, and there's an example of how that works. We're starting this case from A. We go to 3 first because that was the closest. Okay, we now have A and B. Okay, we can go any of the edges that emanate from A or B now that don't take that don't cause a cycle. Okay, so we take C to be the next one because it only has a 1, and that's that example. Okay. So the next section is going to be Kruschal's algorithm when we get down there. And Kruschal takes a different way. With Kruschal, remember the big difference is we're going to order the edges in terms of weight. And we're going to start adding them in that way. Again, not adding an edge between 2 already connected vertices, and not adding an edge that makes a cycle. But otherwise, we're going to keep going to go. So in this way, we've sorted here the list of edges. We start by adding the lowest one, which is the BC, and then we add the next lowest one, which is the FE. Okay, and that's an example of that. Okay. So we didn't cover the section on disjoint subsets and union find algorithms, so you don't have to worry about that. Okay. Next thing should be Dijkstra's algorithm, which we did cover. Okay. Dijkstra, remember, is solving a different problem. It looks similar, but it's not. Dijkstra solves the single source shortest path problem. Okay, so it's from A, let's say, the quickest way to get to all of the other ones. Okay, so in the other example, we did A to B first, and then the second we added was B to something else. But so we counted the distance from B. This is all based on A, wherever we start. Okay, so it all goes back to that. Okay, so they give an example of this as well. There's the algorithm, what it looks like. And here's the example. Again, we start with A to B. Okay, that's the shortest because A could also go to D, but we take the shortest path. Okay, that's the path to there. Now we can pick anything from here. Okay, So we're going to pick this D, B to D, okay? But the distance is not 2. It's all from A. So the distance is 3 plus 2 or 5, okay? And then every step you go through to make sure you still have that optimal position, okay, when you add other things in, okay? It's basically how that works, okay? So Dijkstra is a very important algorithm that we see in networking and lots of problems, okay? Huffman encoding is also an important thing for us to know about. It's the idea of variable length encoding. It's you have to have a frequency of usage. So you have an alphabet, that's all the characters we're going to have to encode. And then you have the frequency each one occurs. And the idea being that you want your shorter ones, the more frequently used ones to have a shorter code. And the ones that are used more have a longer code. Okay, so there are some examples we did of this. We go through and we sort them. We take the two smallest frequencies, combine them together, resort, and keep going. Okay, the idea being the two that are sorted first are going to get pushed further into the tree. So that's why we go ahead and put the smallest frequencies down there. Okay, there's a good example there as well, where you can go through the examples. Okay. So that was it for this chapter. We skipped chapter 10 as well. Again, nothing wrong with it. Just had other things that we cared about. Okay, good thing it was a long one, apparently. There's some interesting stuff in all these chapters, okay? But I wanted to get to 11 and 12. So 11 is on the limits of algorithm power. Okay, so this class, we've done a lot of algorithms that can do pretty amazing things. Okay, but it turns out there are a not inconsequential number of problems that we can't really get to. Okay, that we can't really get a good algorithm for. Okay, so in this section or this chapter, we're going to start off talking about lower bounds, okay, which is an estimate on how much work has to be done at a minimum for a certain type of problem. From that, we're going to be able to try to figure out whether for a given problem, there's an existing algorithm that's pretty close, in which case it's a tight lower bound, or it could be that we're not very close, which is a loose lower bound. Sometimes the lower bounds are what we call a trivial lower bound because we know there's no way we can get anywhere near there. The traveling salesman is one that has such a thing. Okay, so that's the first section. And then we talked about decision trees, which are an interesting technique to allow us to get through a problem. Okay, and then we talked in the last section here on intractability. So we talked about problems being solved in polynomial time. Okay, so here's the lower bound arguments. We can go to see there's a trivial lower bound we can do. There's the informatic theoretic arguments, which looks at how much information has to be processed and how much has to be produced. Then there's this idea of the adversary argument, when you're looking at somebody trying to make things take the longest possible every time they go through, as a way to also figure that. Okay. The problem reduction, we've already saw that before, that if you can convert a problem P into some other problem Q, and you know an answer to Q, then we can do that as long as the cost to convert from P to Q is not too much. Okay. And here are some problems that often get turned into. Okay. So you can get an answer on that. And there's some examples there for that. Okay. Then there's a decision tree. It's just a way to go through to see how many comparisons have to be made in a given problem. So there's a small example of the decision tree for sorting. It gets pretty ugly pretty quickly. Okay, another example there. And we have some exercises from that. And then the really big questions that are left unanswered in computer science is going to be this idea of P, NP, and NP complete. Okay, and we define some terms here about a problem that can be solved in polynomial time which is going to be an n to some number. We don't care what number because there aren't very many algorithms that go over n cubed. Okay, so if it can be solved in polynomial time, we call it tractable. If not, we call it intractable. Okay, based on the input size. Okay, then this gives us two more classifications here. We have P and NP. So a class P then, it's for decision problems that can be solved in polynomial time. Okay, and give some examples there. And then where does it define NP? Must have missed it. Okay. Yes, every decision problem is not, cannot be solved in polynomial time. We have some famous problems here that we've talked about: the halting problem, the Hamiltonian circuit, traveling salesman, knapsack, partition, bin packing, graph coloring, and integer linear programming problems. We've talked about some more than others. Okay, then the other set, the NP, is going to be from the non-deterministic polynomial algorithms. Okay, so these are, I mean, they're better than it could be. At least we can, the non-deterministic part means that we have to kind of guess at the answer, but once we have a candidate, we can in polynomial time figure out if the answer is a solution to the problem. Okay, so that's the idea but you know, with the NP. Okay, so most decision problems are NP. Okay, because NP includes all the problems in P. If you can solve it directly in polynomial time, then you can certainly determine if a solution is correct, or if a potential solution is correct in polynomial time. So we know that down here that P is a subset of NP. Okay, so the big question becomes, does P equal NP? Okay, so that's the issue. Are there problems that are currently considered NP that could be NP, but we just haven't figured that out yet? Okay, so that's the big question we don't know the answer to. Okay, so the other thing about the NP complete, so that's NP. So we have P and NP. Okay, then we have NP complete. Okay, so NP complete means that it's in class NP, and it can be polynomially reducible to every other decision problem in NP complete. Okay, so that's the idea there. So all you have to do is prove that it's polynomially reducible to one of the others that are NP complete, and you get to all the others that way. Okay, so just some more terminology there. There could certainly be some questions asking your understanding of how those terms work. Okay, they're pretty important terms in computer science, and you know, I think it's useful to know them. Okay, we didn't do 11.14 or 11.4 on numerical algorithms. Again, enough in the world without that. Okay, gets us then to chapter 12, which again is a pretty useful chapter. It's basically going to be when we have problems that are difficult, we still have to solve them. We can't just run away, right? We have to have a way to get through them. So we're going to deal with some ways that we can deal with these difficult problems, these intractable problems. Okay, and they're similar in some ways. The first is the backtracking. And the backtracking is going to be used, it can be used for any problem. They give an example here of the n queens problem, okay? And the backtracking is going to work in a depth first fashion. It's going to try something. If it works, it's going to make the next move. So again, this is the 4 queens problem. We start up here at position 0. Position 1, we put a queen here, okay? Position 2, we put a queen in that. We can't put it here. We can't put it here. So this is the first place that we can. Okay. But if we do that, it all fizzles out. So we go back to this one, make the other choices. In fact, this whole branch fizzles out. So then we have to go back to, well, if instead of being here, What if it's here? But see, this is the fifth box that we make, okay? So that's how that works. There's another example here with the Hamiltonian circuit problem and the subset sum problem. Okay. And then we got to the branch and bound was the next thing that we do here. And branch and bound here is going to be for problems that are optimization problems. They're looking at the max and the minimum of something. Okay. So for that, we can go through and see if we're getting better or not. Okay. So comparing it, we have to have this way for every node in our state space tree, a bound on the best possible solution if we keep adding components. Okay, it's probably that upper bound's probably not going to be obtainable, but going down a path, we're going to pick the one that has the best upper bound. Okay, so these work in a breadth first fashion. So you look at all the options you have from a particular node. You take the one that's the best, kind of go from there. Okay, they do an example on the assignment problem. And these tend to take the form of, we start at 0. What's the best it could be? The best is the each person doing the cheapest jobs. Okay. Then we're going to say, well, what if person A takes job 1? I think it's jobs. Yeah, person A. It could have been a job A. So we're going to say, what if person A takes job 1? Then what's the lower bound? What's the best the rest could be? What if person A takes job 2? What if person A takes job 3? What if person A takes job 4? Okay. And from this, you can see that person A taking job 4 here, no, sorry, person A taking job 3 is the one that has the best bound. Okay. So, oh, sorry, this is a minimization problem. I went the other way. It's not the knapsack. Yeah, this one we're going to take, they're going to take job 2. We're trying to minimize the cost. Okay. And then once person A has taken job 2, we have 3 choices there. B could take 1, B could take 3, B could take 4. We look at these and see that B taking 1 is the lowest number. Okay. So now we're going to say B is taking 1 is our option. And then from there, you only have 2 options. So you just work them out. Okay. So C can take 3 and D can take 4, or C can take 4 and D can take 3. Okay. And when you do that, you see that the cost of this option is the best. Okay. So following this tree, we have A takes job 2, B takes job 1, C takes job 3, and D takes job 4. Job 4. That's the best, the optimal solution. Okay. And then we'll provide an example of this. I did a video of this. This one we're looking to maximize our values. Okay. And some of you had some trouble with the formula here, but what this is saying is the value of what you've added to the bag so far. Okay. That's what this is. Okay. This is going to be how much weight capacity you have left. Big W is your total weight, and this W is what you have so far. So you're saying you have 5 pounds less or 10 pounds less or whatever. Okay. You're going to multiply that by whichever this best value that's remaining is. Okay. Assuming that every pound that you have left, you're going to be able to get it at the best value to weight ratio, which of course you can't, but that's the idea. Okay. So that's how those problems work. Okay. I could certainly give something like that. Here's one with the traveling salesman, just a different way to calculate the either upper bound or lower bound. Okay. And there's the homework there. Okay. And we didn't do 12.3. So 12.2 is going to solve that for us. Okay. So that's it. That's the test. So the test should go live. I think this week, hoping it works out with people, I'm going to have office hours on Tuesday. So it'll be Tuesday at 7. Okay, if you have any final questions. And my goal is to make the test available Wednesday, Thursday, and Friday. Friday's the last day of class, and there's no finals week for this class that I can figure out. So I think I have to have you turn in the test by Friday. Okay. If that's a struggle for some in some way, send me a message and let me know if we can do something different about it. Okay. So that's it. So make sure the forum, I'll add a forum right now for any questions about the final or anything so far. If you have any questions about the homework problems, things, how I've graded, how it worked, there should be solution manuals, I think, for everything except 10. 10's due today. So I'll make sure that there are solution, either videos or sheets, one or the other, to make sure that you can check your answers. And if there are questions, make sure you let me know.